So Matteo Baggioli will resume his second lecture. So please, Matteo, you can start now.
Okay, so welcome back. Before start with the second part, I would like to ask if there is any question or anything that you want me to repeat or to discuss about the lectures of yesterday. No? Okay, then let's move to the lecture of today. So the lecture of today will be focused on a different type of phases of matter that are liquids or viscoelastic, and they are different in nature, and we will see in which respect with respect to the solids that we discussed yesterday. So these are some of the basics literature and references that might be useful for you if you want to dig more into the details. So these are, very standard textbooks, and this is also a quite famous lecture on hydrodynamics. So again, let's start as yesterday from the very basics, and then we will go higher and higher in details. So what is a liquid? Well, a liquid, contrary to a solid, is phases of matter whose shape is not fixed, but whose volume is fixed. So you can see, for example, the liquid inside this glass. Now, the main difference with the solid is that the liquid is not rigid, but rather viscous. What does it mean? Well, we saw yesterday that the main characteristic of a solid is the property or the ability to have a response in function of basically a static strain. So you do a static deformation and the solid responds with what is called elasticity. Now, a fluid is different. A fluid responds only to what is called a shear strain rate. So what is important for a fluid is not the static shear, but it's actually the rate of deformation. And the standard formula that appears everywhere is basically the definition itself of the viscosity. So the viscosity is nothing else than the coefficient of proportionality between the strain rate and basically the stress. Okay, so this is the typical picture of the two layers of fluid that we are shearing at a constant speed, and we want to compute basically the friction or the force transverse to this shearing. And the mode that arises usually in liquids because of this response is diffusion. And the typical example is shear diffusion. And by diffusion, I mean just a mode for which the displacement square follows this kind of rule, so linear in time, and the coefficient is called the diffusion constant. So this is the typical picture that you see if you throw, for example, some powder or some colors in a glass of water. Now, the typical theory to understand and describe fluids is hydrodynamics. So what is hydrodynamics? First of all, I would like to make a little remark about the name hydrodynamics. So different communities and different people refers to hydrodynamics as different things. So for example, if you talk to your condensed matter friend and you tell them that you have an hydrodynamic theory of solids, they will laugh in your face because it looks quite hot, right? Hydrodynamics seems to apply to fluids. Why we did hydrodynamics for solid? So here, what we mean by hydrodynamics is something, let's say, more extended. It's just the description of the system at large distances and late time. So imagine you have a system, for example, these waves with this surfer, was characteristic, let's say, microscopic length scale, we call it A. Now, hydrodynamics is everything that refers to these systems at length lambda, which are much larger than A. So if we want to translate this in Fourier space, this just means that we are considering small frequency and small momenta to the characteristic energy scales. And the characteristic energy scale, if you are in a system at finite temperature, is clearly given by the temperature. So we want basically these kind of assumptions. And this is reflected, if you like, in a gradient expansion, because every factor of frequency and momentum is nothing else than a time derivative or a special derivative applied to your fluctuations. So basically, when we are doing hydrodynamics, what we are doing is we are doing an expansion in mode which are slow and then slowly faster, okay? And we want to keep only the leading. So this is a perturbative expansion in derivatives. And this is basically the basics to describe fluids. Now, again, let me just focus.
Matteo?
Yes,
Can you go back?
sure.
Okay, so here you mentioned the energy scale is given by temperature. So what happens if the system has charge density or magnetic field? Do you need the frequency is much smaller than all energy scales?
Yeah, that's correct. Yeah. So the frequency must be the other energy scales can be interplayed as much as you want. Like you can have, one bigger than the other, whatever, but the frequency or the momentum has to be always the lowest scale. Yeah.
Okay,
that's correct.
Much smaller than all energy scales in order to make the hydrodynamic to work. Okay, I see. Thank you.
Because basically what you want to do is you want to suppress all the corrections that come from, let's say, charge square or things like that.
Okay, I see. Okay, thank you.
Yeah. Now, the typical example, let's spend maybe some words more for those of you who are not very familiar, is diffusion. So diffusion appear in fluid in the transverse sector instead of the propagating phonons that we were discussing yesterday, and is intimately linked to dissipation and to viscosity. So how diffusion is extracted usually in hydrodynamics is very simple. So hydrodynamics is also the theory of conserved quantity. And so we start usually from a conservation equation, which is basically this continuity equation. And then what we have to assume is something else, which is basically called the constitutive equation. So we have to assume basically an expansion, in this case for the current, but in general for every object that we want to consider, in derivative. And you will see here that, for example, this is the first expansion. So this is the first term in derivative that you can write. And if you just basically plug this expansion inside this equation, you get, and you go to Fourier, you get very simply that the mode looks like this. So this is a purely imaginary modes, which disperse with a law which is quadratic in momentum. And this is what I will call diffusive mode, okay? And the typical example is relativistic hydrodynamics. So in relativistic hydrodynamics, this is happening, and the diffusion constant is actually set by the ratio of the viscosity to the entropy, and in simple system like conformal system and relativistic is just the inverse of the temperature, because the temperature is the only scale available. Now, why fluids are somehow different from what we discussed yesterday? Well, you can already see now why they're different, because the approach is totally orthogonal to what we were doing. So as I was showing just now, you can see here, we don't start from an action. We don't start from a field theory. We start directly from some conservation equation and some constitutive equation. And that's exactly what you do usually in hydrodynamics. So imagine, for example, you have a system with one current and the stress tensor, which is always there, and both are conserved. And then you assume this equation and you start making an expansion of these terms, which of course is dictated by the symmetry of the system. So which kind of term you can put here is just a matter of the system, of the symmetry of your system. And that's it basically. So then basically you run your machine, you plug this inside here and you go order by order in expansion. So this is very different from what we did. And the main question is, where is the action, right? Can we do some more formal field theory for hydrodynamics? For example, what is the action for a diffusive mode, right? We know pretty well what is the action for a propagating wave, right? It's just the Klein-Gordon equation. What is the action for a diffusive mode? And the main problem, which is basically behind this issue, is that dissipation and emission action do not like each other very well. And I will discuss in a bit how basically you can avoid this problem, or which kind of solution you can think about it.
Hi, Matteo.
Yes.
Hi. Can you comment on how to describe the physics of fluid, of liquids at the scale of mean free path?
Yes. So in terms of the mean free path, basically it's similar to this kind of discussion. So imagine you have, let's say, a particle with a certain mean free path, and the mean free path is basically producing, imagine, for example, the mean free path, it's the mean free path of momentum non-conserving things. So imagine, for example, you are an electron and you are moving in, say, your graphene sheet, and you bump on impurities because impurities are there. And this defines basically the mean free path. Now, the mean free path defines for you basically the microscopic scale, right? Because basically the things exist only inside this mean free path, and that's it. Now, if you want to do an hydrodynamic description, you need to take distances which are basically larger than this mean free path. And that's basically the same story. So
yeah,
you want
true.
to
And
always,
the conservation equation should always true, right? At any scale. So,
well, it depends a bit, right? Because if you have, for example, imagine you have a system which does not conserve momentum, which is the case, for example, for electrons bumping on impurities. Of course, momentum is not conserved. And that's how you define the mean free path, right? Somehow. So there is a relaxation time, and the mean free path is just the relaxation time times the drift velocity.
yeah, that's
right?
true. That's for the, I mean, not for the conserved current.
Yeah, exactly. For example, something like that. Now, the point is that in order to look at hydrodynamics, you have to look at basically distances which are larger than the mean free path. And this corresponds exactly at looking at time which are longer than the relaxation time.
Yeah, I agree. I mean, so hydro, I mean, in this kind of framework, there are two constitutes. I mean, one is the conservation equation, another one is the constitutive equation. I mean,
yeah.
The conservation equation doesn't depend on the scale, but the constitutive equation depends on the scale. Is there any possibility to go beyond, I mean, go beyond this derivative expansion for the constitutive equation, that kind of effective field theory? I mean,
yeah, so I will show you in a while. So that's why basically people were not very satisfied about this, because it looks a bit like by hand, in the sense that, yeah, you follow the symmetries, but you don't have a principle, an action, right? Something more robust that you can derive everything. And that's what people more recently did. So they construct an action and then you can just do the standard field theory formalities and you get basically all your hydrodynamics equation. But this needs
and that theory applies for the scale, I mean, at over the mean free path or much smaller scale. Is this true?
No, I don't think so. I mean, you can account, of course, you can always make corrections, right? But basically, that's basically the question about the convergence or the breakdown of hydrodynamics. So this is a big question. So where hydrodynamics break down, right? At which point? And I'm not an expert on this, but I think the question is still kind of open. So it's not so clear, right? So for example, we know that in holography, because of this strong coupling, hydrodynamics seems to work much better than what it should, right? So it applies at actually time scales which are shorter than what hydrodynamics should apply. So that's definitely a very important question. So I will make a little comment at the end about the convergence, but I don't believe it's a totally closed question. So it's definitely relevant.
Okay.
Yeah. Thanks for the comment. So we were, here. So this is the big problem. And then we want also to do something more than that, right? Because a perfect solid and the perfect fluid are definitely some kind of theoretical abstraction, right? So in general, any system is viscoelastic in the sense that it combines an elastic and a viscous response. So here I just put some picture, for example, of common things which are viscoelastic. So for example, the cheese on your pizza, your skin, and the foam that basically of your pillow, etc., etc. All of these are material which combine elastic properties with viscous properties. And the dynamics become more complex. So let's see how it look like. So remember that the main point to study all the mechanical deformation is always the relations between the strain and the stress. So deformations and forces, right? This is the key. So imagine I now take my material, my pizza, and I bend it. So I produce a strain, okay? And this is the kind of strain that I want to produce, a simple one, just a step. Okay, so if the material is totally elastic, we learned yesterday that basically the strain is proportional to the stress, right? It's just pure proportional. And therefore, what you will see is that the stress is just basically the same shape multiplied by a constant, which determines how rigid is the material, right? So this constant here, sigma 0 and epsilon 0, are not the same, but the shape is exactly the same. This is what we will call an elastic material. Now, if you have a viscoelastic material, this is not true anymore. And what happened is a shape like this, where basically the stress piles up, but then you have a relaxation, which is determined basically by the viscosity. So viscosity means dissipation, and that's why basically in time, you are basically decaying, the stress is decaying with a relaxation time, which is actually the ratio between the viscosity and the elasticity. So if the viscosity is 0, this relaxation time is basically infinity. So you will never go down. On the contrary, if you have basically 0 elasticity and only viscosity, remember the viscosity is proportional to the time derivative of the strain. And the time derivative of the strain, if you see this plot, is non-zero only here. So if the material is perfectly viscous, you will have only a delta function here and nothing else. Okay, and this is the interpolation between the delta function and the elastic behavior. So now why I'm telling you this? Well, because you can do experiment and you can actually see this in real life. So what is the typical experiment, for example, to study viscoelastic material and to study solid and fluids? Well, it's very simple. It's this kind of experiment here. So you take 2 plates and you put inside your material, imagine, I don't know, the toothpaste. And what you do is you apply a strain deformation. So for simplicity, what people do usually is to apply a periodic deformation, like a sine deformations, and you measure the stress response, okay, just here. Now, again, what happened? Well, what happened? If you are in a perfect solid, again, as we said before, the 2 stress and strain are just proportional. So you will see no out of phase thing, right? It's just completely in phase, completely perfect. Now, on the contrary, if you have a viscous fluid, you will have a totally out of phase signal, which basically it's the manifestation of the dissipation. And if you are in a viscoelastic material in general, you will have a signal which has a certain phase, which is between 0 and pi half, and determine how much viscoelastic is the system. Now, to be a more quantitative, what you really do usually is you write down the stress and the strain as 2 basically oscillatory functions with a different amplitude and importantly with an angle, with a phase shift. Now, in terms of viscoelastic, let's say, literature, what people do is they define what is called the complex modulus, which is basically just the ratio between the stress and the strain. And it has a real part, which for historical reason is called G prime, and an imaginary part, which is called G second. Now, G prime is the non-dissipative part. So this we refer to elasticity, and this we refer to dissipation. You will see because that's an imaginary part. Now, in our language, this object here is nothing else than the 2-point function of the stress tensor. Okay, so you can see very clearly this is the source, and this is the response, and this is just linear response. So this is just nothing else than the green function. And this is what I was telling you. So you have 2 components, and you have an elastic response, which is static and in phase, and the viscous response, out of phase. And this is what you usually see in experiments. So this is a system which is fluid, and you can see what happened in function of the frequency. So G prime, which is the real part, is basically 0 at 0 frequency, and then it grows. And G second, which is the imaginary part, grows linearly, okay, with the frequency. And this shape here is basically the viscosity of the system. Differently, in systems which are mostly solid, the real part is more or less constant, and it's much, much larger than the imaginary part. So dissipation is very small and can be basically neglected. So this is the typical kind of response. Now, the main questions that I want to ask today is, okay, what is really the difference at the end of the day between liquids and solids? Are they really different? And what is just a matter of scales, or is something more? Well, the first observation, which goes back a long time ago by the Russian physicist called Frankel, is that liquids and solids are definitely not different if you consider high frequency, or frequency bigger than the inverse of this relaxation time that I will describe in a second. So this is proved in several experiments, and you can prove it very easily, but just by jumping from a very high trampoline, okay? And here you can see, for example, one experiment in water, and this is like a scattering experiment, and what you see is that at high frequency, you see basically not only the peak of the longitudinal phonon, but also the transverse. So this is not a big surprise, okay? This is understood like a lot of years ago, no problem. Now here comes the thing which is a bit more surprising. So here, this is an experiment done by the group of Laurence Noiret in Paris in 2012. And so what they did here is exactly the experiment that I was commenting before. So they did a shear strain and they measured the stress, and this is what they get. So as you can see here, shear and stress are totally in phase, right? And here, G prime, which is the real part, is much larger than G second, which is basically almost 0. You can see this is a logarithmic plot. So this is basically 10 to the minus 1, okay? So from these things, you will say, well, okay, fine, you measure the viscoelastic response of a solid. Well, the only problem is that this object was water, okay? So this was what we usually call a liquid. So what is the problem? What is going on here, right? So in this paper, they claim that liquids support propagating shear waves, so phonons, transverse phonon, also at low frequency. And this is very weird because it goes totally against our intuition. It looks like liquid behave like solid at low frequency. So what is the catch? So the catch, and we will see in a second, is in this value. So this value here is the length scale. And the point is that the length scale here that we are considering is actually very small. And I will show you in a while a full theoretical model to understand why, in these cases, it makes sense, or at least we can understand why liquids looks like solid. Now let's think a bit more about liquids. So what is actually a liquid? So a liquid is a collection of particles, of molecules, if you like, that moves. So they move in two different ways. So let's start from, first of all, at the descriptions in terms of the real physical space-time, the real liquid. So you have these molecules, and these molecules, they jump around, right? So they move around with a certain time, but they also slightly oscillate, like around the position. So if this was a solid, all these molecules, all these points will only oscillate around the equilibrium position and will not jump anywhere else, just because they're bonded together by the lattice, right? Like we were discussing yesterday. In a liquid, it's different. People can jump around. And at the level of the potential, this means that imagine that you have a kind of potential with a lot of minima. So every minima is basically the equilibrium position of each molecules. And then what you can do usually in a solid, right, you oscillate up and down in this minimum. And this is what produces basically the phonon. But in a liquid, what you can do, you can also jump across the potential. And you can jump on the other position. And this is exactly what the molecules do. And in order to jump, you have to jump a potential barrier. And what we can define is basically the average times of rearrangement, which corresponds to the average times of these jumps. So in a solid, this average time will be infinity. So particles will never, or very, very rarely, jumps between one position to the other. In a liquid, this is much more common, and it happens much more often. So this is basically the scales that determines is how much molecules rearrange around. Now, why this is important? Well, this was noticed already by Maxwell and a very famous physicist a long time ago. So the question is, okay, how can I add basically this kind of jumping behavior in my equation? So let's look at this equation. So let's forget of this jumping time. So the equation that we have is a very simple equation, which is the equation of a wave, right? So it's a wave equation that describes, if you like, your phonons, and your speed, as we were discussing yesterday, is determined by the rigidity of the system. Now here, what they did, Maxwell and Frankel, was, okay, let's assume in a fluid there are also these jumps, and let's put at this, for the moment, just by hand, a terms which takes into account these jumps. Now, if you solve this equation, you get this kind of solutions, which is of course complex. And you get a very peculiar behavior. So let's see what you get. So if I plot the real part of this frequency here, what I see is that till a certain momentum here, which is basically defined at the momentum in which this guy becomes larger than this guy, there's nothing in the real part, okay? There's absolutely nothing. Then at a certain momentum, this square root becomes positive and a guy appears. And you can see here, this is a propagating guy. So this point here is just in the literature called K-gap, because it's a gap in momentum, in analogy with the gap in frequency. And it's quite interesting because you can see what is the physics here. So the physics here, it means that if you go at very large momenta, let's say here, basically hydrodynamics is of course not valid anymore. And what you see is the behavior that you will expect in a solid, right? A propagating wave. On the contrary, if you go to small frequency, you see that basically you see the dynamics of a fluid. And this is more, let's say, evident if we look at the imaginary part. So if we look at the imaginary part, what you see at low momenta is that basically you have one diffusive mode, which is exactly the shear diffusive mode, and one non-hydrodynamic pole. And at a certain point, these modes collide and they produce basically the propagating guy, okay? So this is interesting because it violates what I told you before. Remember what I told you before, that only at very high frequency you can have propagating waves. This is not true here, right? Because at high frequency, so let's say here, of course you will have propagating waves. But if you go down, you can have propagating waves also at small frequency if your momentum is larger than this number, okay? So this is basically a theoretical mechanism that could explain in principle what we saw in that experiment. Now let's investigate a bit further what this means. So this means that if you look at the fluid, there is a specific length scale, which is characterized by basically this K-gap space, which is inversely proportional to this tau. So let's go here back a second. So this means that this point is the inverse of this jumping time. So if this jumping time is infinite, like in a solid, this guy will approach zero. So this way we start from zero and we will get our standard phonons, nothing fancy. On the contrary, if tau becomes basically super small, so basically molecules rearrange very fast, this guy will be thrown away at very large momentum and the physics will be basically the physics of a liquid. And on the contrary, if tau is some finite number, let's say order 1 number, you can have a transition between these two behaviors, moving the momentum. So this means that depending the scales at which you're looking in your experiment, you will see something that looks like a fluid or something that looks like a solid. And this is exactly a bit the idea. So this guy is a fluid if you look at distances which are actually much larger than c tau. And this go back basically to the question of Jan somehow. So you can imagine that this tau is nothing else like the mean free path, if you like. And these distances, sorry, this c tau is basically kind of the mean free path. So it's the propagation length of the phonon. So the phonons can propagate only at these distances. So inside these kind of spheres, in these scales, phonons can propagate. If you look at higher distances, phonon will disappear and you will see just diffusion. So this is a kind of crossover of that kind. And this distance is just defined as in standard, let's say, just by dimensional analysis, by the speed, which is the elasticity, times tau, which is this jumping time. Now, there are more evidences of this system. So the first evidence was found by my Kunesmacher colleague in a PRL paper of 2017. And what they did is they did molecular dynamic simulations for fluids. So what you do is you take a huge amount of basically particle interacting between themselves with a certain potential. Usually the choice for fluid is a Lennard-Jones potential. And then you plug it in a big computer and you let it evolve, okay? And then, of course, once you have the full evolution, you can check, for example, the correlation functions. And from there, you can extract the dispersion relation, etc. And this is what they see. So you can see here, this is, for example, a simulation. And you can see that the frequency starts more or less from a finite K value. And the shape looks like pretty similar to what we were discussing. And the other funny thing is that increasing the temperature, this shape goes more on the right. And this makes sense if you think about it, right? Because the more the temperature, the easier the jumps, right? Because you have more energy. So you will over jump the potential and therefore you will look like more like a liquid. That's very understandable. Now, another interesting thing is that we never before made any statement about the scales. And here you can see, for example, already in the simulation that scales appear. So this is more or less the inverse of an Armstrong, to have an idea of how small you have to go to see basically a solid in a liquid. Now there is more. Recently they did experiments. So this is a neutron scattering experiment on gallium. So gallium, it's a simple liquid, and you can see the experiments here with the error bars and everything. And you can see basically a different temperature that, again, this kind of shape seems in agreement with that simple theory. Now, this is very nice, and but we wanted to understand this a bit more from the theoretical point of view. So before I move, is that clear? Is there any question or something that you want me to explain more before I go to more theoretical topics? Okay, then let's move on. So the first question that I would like to do is, okay, I want to have some kind of field theory model, right? Because I know very well how to do a field theory model for, let's say, a wave, right? It's just Klein Gordon. And can I do something, including this relaxation time? And despite the question in Fourier space looks very simple, it's actually a very hard problem to understand this from a field theory point of view. And I will go, and that's exactly for the same reason we were discussing before, because we want to include dissipation. So the idea that we had is the following. So we have to include something like the viscous force, okay? And the viscous force looks like some time derivative, some single time derivatives. And then what we thought about it is, okay, let's try to put a terms with a single time derivative, right? So the first problem that you encounter, and it's actually that there is a lot of physics behind this problem, is that if you do that with a single field, you will realize immediately that you cannot do it. The reason why is that if you do a terms like this for a single field, this is just a total derivative, right? It's just a derivative of phi squared, and you can just throw it away. So this is already a funny feature that in dissipative system, what you need is copy. So you need two scalar fields, okay? And that's exactly what we try to do. So then what we try to do is, okay, well, let's try to put two scalar fields, or if you want, you can recast this in a complex scalar. And let's put a term like this. Now, a term like this, it's clearly a dissipative term because it has only one derivative in time and is clearly non-Hermitian. But importantly, it's PT symmetric. So now I want to emphasize the fact that you need to have two fields. So this is actually not a surprise at all. And it cannot be understood very well using what is called the Keldysh-Finger interpretation. So Keldysh-Finger interpretation or Keldysh-Finger formalism is the formalism to do basically field theory with dissipation. And the main idea to do this without entering too much in the details is that in your action, you have always to make a copy of your field, which corresponds somehow to a copy of your field propagating on a contour which goes back in time. So instead of having the usual path integral formulation, let's say for one field going in time, you have to do a contour, which is a bit weird, which comes back in time and put basically a copy of your field that goes back in time. Now, this kind of construction, again, is clearly non-Hermitian, but importantly, if you assume PT symmetry and the system is still unitary. And what is the picture? Well, the picture is that somehow you have a big system, which is composed of two subsystems. And one of them is kind of gaining energy, and the other one is kind of losing energy, but they are coupled together in a way that basically the things that this one is gaining can be transmitted to the other system, and you can reach a situation where actually this is in equilibrium, okay? And once you reach that, basically the eigenvalues of the system are totally real, and the system is totally unitary, and the evolution makes sense. Now, there is an important, at least one simple computation that I like a lot, which shows you why basically a non-Hermitian Hamiltonian introduced dissipation, which is basically this simple equation. So let's go back to our quantum mechanics and let's take the time evolution of an operator. And well, the time evolution of the operator we know very well, which is the commutator between the Hamiltonian and the operator. And well, we write it here. So now it's clear that if the Hamiltonian is Hermitian, H dagger is the same of H, and this is 0. So unless you put something that does not commute with the Hamiltonian, obviously these things is conserved. But this is not true anymore if the Hamiltonian is non-Hermitian, because basically these terms do not cancel. These terms actually will give you the imaginary part that you have in the action, right? So if H contains, for example, some imaginary term, the real terms cancel because the dagger of real is the same, but the imaginary part will remain and will give you basically a relaxation time. So what we did then when we did this field theory, well, we wanted to study and to see if what we get from the field theory makes sense. So the first thing is we computed a two-point function with standard field theory method. And here you can see what we get. So the first thing which is interesting is that in the denominator, so the poles of this green function agrees perfectly with basically the equations that we were discussing before. And of course, we can go also in real time and we can see two things which are kind of expected. So here you can see the evolution of time of the two-point function. And for momenta which are below this point and momenta which are actually above this point. So remember, below it's a fluid, above it's a solid. Now you can see that above what you see are oscillations. And this is totally expected when you have some wave propagating, right? You get just basically a sine oscillating, nothing fancy. The funny thing is that when you go below this point and you are in a fluid, oscillations completely disappear. And you get basically a decaying mode, which is expected because it's just basically the relaxation of the fluid. And to do more, you can actually do a step more and study the interaction potential. And basically you can study the two regimes and you find a very similar feature. So you see oscillations in the solid-like regime and you see a decay in space, in this case, in the hydrodynamic regime. So let me tell you a bit more about these equations because it's quite interesting. So first of all, this kind of equation is an equation that appears in a lot of systems. And we had recently a review about this. I will mention it at the end. So one typical system where this happens is relativistic hydrodynamics. So relativistic hydrodynamics, let's go back to basically this diffusive mode that we were discussing. We know that at linear order in the transverse sector, we have diffusion, and this is shear diffusion. Now, there is a problem that people complain a lot in the past, which is, well, this mode, if it's assumed to be forever, it will basically lead to a violation of causality. Why? Well, because you compute the group velocity, and this group velocity grows like the momentum, and there will be a certain momentum at which this will be faster than the speed of light. Now, in my opinion, this is not a real problem because it's based on an extrapolation which is not natural at all, but it's a big issue for simulations. So for example, if you want to do a simulation of, let's say, quark-gluon plasma, what you do is you put the initial boundary condition as relativistic hydrodynamics, and if you put this as initial boundary condition, your laptop will explode immediately. So what was the solution? Well, the solution, which was introduced by Israel Stewart and also by Cattaneo, is exactly like the same. Let's put a term which regulates this behavior. And the terms look like exactly like a relaxation time. Actually, Israel and Stewart derived these terms from hydrodynamics. So these terms appear in hydrodynamics if you extend basically this computation to higher order. So you go one order more and you find that basically these terms arise. And this very nicely is the same equation that we were discussed. This equation, you can find it also in a lot of places under the name of telegraph equation, because it's exactly the same equation that appears in certain circuits describing a telegraph. Now, this was a bit the long, let's say, introduction about what is known in condensed matter field theory and whatever. And now, of course, since we're here, we want to study if this is happening and what holography can tell us about this behavior. So the first step that you want to do is you want to take the simplest solution that we know, so the Schwarzschild black hole, and analyze what happened. So it's often claimed that the Schwarzschild black hole is the dual of relativistic hydrodynamics, right? And here is the modes that we see in a Schwarzschild black hole. So here you see that basically there is your shear diffusive mode, which has 0 real part. And then there are a bunch of modes which are non-hydrodynamics. So they have a finite relaxation time and they are gapped. Now, quite interesting here, you don't see anything like I was discussing before. As you can see here, there's no propagating wave appearing and there's no collision. So here, instead of a collision, there is actually a crossing. Now, let's try to go to a little more complicated model, and let's try, for example, to add a scale. The simple example is the linear axion theory. So if we do this in the linear axion theory, we discover that the behavior is modified, and it looks like very similar to what we were discussing. So these are the modes. This is actually, sorry, this is a bit imprecise. This is the real part of the frequency. And this is in function of t over m. Notice that now, since we have an additional scale, we can actually move these scales with a meaning. And once you move the temperature, what we see is that you see a gap opens, and basically it goes to the right, and to the right, and it follows very well the theoretical expectation. So for example, here, just for the highs, this is a comparison with the simulations, right? At least the qualitative behavior is totally consistent. And then from this, remember that this point is proportional to the inverse of this emergent relaxation time. And we can compute the relaxation times in function of basically the inverse of the temperature. And we see this law, which is kind of universal law. It's called Arrhenius Law in liquids. And that's what you see here. So this is, for example, an experiment that does exactly the same thing. So it looks like holography is kind of consistent with what we were expecting. And there are many more instances that actually we found where this kind of equation arises. So one interesting instance is when you consider Coulomb interaction. So let us consider now that the magnetic and electric field are not external sources, but they are like dynamical fields, okay? And in order to do this in holography, what you have to do, you have to slightly change the boundary condition for your fluctuations in this way, where basically this parameter lambda here determines the coupling of the Coulomb interaction. So this is the leading and this is the subleading. Okay, so usually what you do to compute the quasi-normal mode, you just set the leading to 0 and you forget about this. Now this is a kind of mixed boundary condition that mix the leading with the subleading in this way, the specific way. This can be derived, and is derived actually in this paper and in previous paper by my collaborators. And when you do that, you go to the modes, and again, you find very funny feature. So you can see again that you see exactly this kind of behavior. And here you see the collisions. And not surprisingly, these kind of collisions and appearance of a relaxation time can be understood very simply using magnetohydrodynamics. So magnetohydrodynamics is just basically the extension of hydrodynamics when you consider the magnetic field and the electric field as dynamical. And it's done in this very nice paper by Koftun and Juan Hernandez. And there you can see the expression, and the expression are in total agreement with basically this behavior. So the Coulomb interaction basically produce a relaxation time for these modes. Now, yes.
Can you go back to the previous slide? So what is the next one? Sorry.
This one?
Yeah, this one. What is the difference between the colors?
Oh, the difference between the color, we are changing the chemical potential.
So which one is the chemical potential case?
Sorry?
Which one corresponds to the zero temperature case, zero chemical potential case?
Let me remember. I think it's the blue. Is the zero chemical
corresponds to the sugar shield black hole case. Am I right?
Yes, exactly. Yeah.
Then that means there's no K gap in that case.
That's a very good point. So here there is a caveat. The caveat is the following. Here we have a gauge field, and when you put the gauge field at mu equals 0, you don't get exactly the Schwarzschild. You get Schwarzschild plus a decoupled vector on top of it.
Okay.
So basically this mode here is not a mode of the metric, but is the mode of a probe vector on top of Schwarzschild.
Oh, I see. So basically
that's why you didn't see it before. So you didn't see it before because before I didn't have that gauge field.
I see.
Yeah.
Okay, thank
That's
you.
the point. Yeah. So yeah, then
may I ask some question?
Sure.
So you add the linear action.
Yes.
Linear action. So my question is, what's the dual interpretation of the linear action in the language of dual field theory?
Very good question. It's actually a very hot topic. So my interpretation, so people likes to say that this is a kind of homogeneous disorder, whatever. My interpretation is that it's an effective field theory that describes basically momentum dissipation. So you introduce by hand a momentum relaxation. You don't know where it comes from. So you have absolutely no idea if this comes from Hump-Clapp disorder or whatever. It's just a coarse-grained description that does not capture the microscopic. So I think it's a bit nonsense to try to do a microscopic interpretation of this model, because the only thing this model is actually doing is putting a relaxation time to momentum. It's exactly like the Drude model, if you like. So for me, if I have to tell you, the linear axiom model is the equivalent of the Drude model, nothing else.
Okay.
And in the Drude model, basically what you are doing, you are putting by hand the relaxation time there. And okay, you can say it comes from bumping, whatever, but it's very phenomenological, right? You don't have a microscopic description of that.
Okay, thank you.
Yeah. Welcome. So yeah, then, so the next step is to try to find out what is the real motivations around this, basically this behavior. And there was a very nice paper by some known people in the literature, which states the following. So what these people state is the following thing. So hydrodynamics, by definition, is usually the theory of conserved quantity. Okay, so you have a bunch of conserved quantity, and hydrodynamics is just the dynamical evolution of this. Now imagine now that one of these charges for certain reason is not conserved. Okay, and you can see here, so we put by hand that one of these charges has a relaxation time. Okay, these relaxation times can come from basically the breaking of some symmetry, right? So the symmetry associated with the conservation of this object is softly broken, and that's what we get. Now, if you do the computation, this author showed very elegantly that this is enough to basically have an equation which looks exactly like the one we were discussing. So the picture is this way. You have a bunch of objects which propagates and do not relaxes. They are just conserved quantity. But you have one guy that instead of just propagating forever, relaxes in a very long way with a time scale which is very long. And what they prove is that that equation comes immediately because of that. So whenever you have this kind of situation, it doesn't matter which kind of situation it is, that's what you get. And indeed, all the examples that I showed you before enters in this kind of this discussion. So for example, for the linear axion, this would be the momentum relaxation scale. For the magneto-hydrodynamics, this would be the relaxation scale introduced by Coulomb. And we will see other examples. So in the liquid example that we were discussing at the beginning, this would be the time of jumping between the minimum of the molecule, et cetera, et cetera. But this is a very nice general, let's say, symmetry argument. And this was formalized also in the context of global symmetries, which are usually related to two-form dynamics. I don't want to spend too much time because, of course, there are a lot of details. But basically, you can construct a holographic model and also not holographic model with this global symmetry, which are important for several, let's say, topics. One of them is magneto-hydrodynamics. The other one are systems like elastic systems. And what you get is that in general, whenever you slightly break this global symmetry, you get this picture. So here you can see, for example, these two papers, and these are just plots that I stole from those papers, and you see the dynamics is exactly the same. So this dynamics is very universal. That's what I want to convey. And there is another thing which is related also a bit with what we were discussing at the beginning, is that this dynamics, so this bumping of two modes, seems to be very important for a very relevant theoretical question, which is what is the convergence of hydrodynamics? And what is the radius of convergence? So hydrodynamics is a perturbative series, like basically all the series expansion that we have in field theory or in physics. And an important question is, how much can I trust it? So how far can I go, right? Will my result become better and better and better, or at a certain point will collapse? And where it will collapse and why it will collapse? And so there was a lot of discussion because at the beginning people, including myself, tried to show that basically the radius of convergence of hydrodynamics was 0. But then there was a paper by Kovtun, Grozanov, Starinets, and friends where they claimed that actually if you go to momentum space, the radius of convergence is finite. And then there was a big fight to understand, is it 0 or is finite the radius of convergence? And there was a recent paper by Heller and collaborator, which basically put a solution to this problem. And the solution has a lot to do to the K-gap. So actually the position of the K-gap, so the position at which this collision happened, is exactly the one that sets the radius of convergence of hydrodynamics from a formal perspective. So what you can see here is the following. So what they do, so here, first of all, you can see basically this collision in the complex plane. And here you can see a plot taken from this paper by Heller, which was this year paper. And what they see, what you show here is basically the behavior of the coefficient. So this is the behavior of the coefficient in function of basically n, so the number of the expansion. And this is basically if you are below the K-gap or if you are above the K-gap. So basically you put some boundary condition that has support on the momentum in the initial condition. And this support can be only for modes which are below the K-gap or for everybody. So if you put it below, what you see is that basically these things converge. So these guys, you see at a certain point, they stop to grow and they basically become flat. On the contrary, if this does not happen, you see, so this is basically the ratio between one coefficient and the next. So if this ratio becomes larger than 1, this clearly means that your perturbative series is not working, right? Because the n+1 coefficient is becoming larger than the n coefficient. So this means that the more term you are adding, the worse actually you are getting right? After a certain number. So you can see it immediately here that basically after a certain number, things is getting worse. So you compute your result at first order, very nice, nicer, 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 and then at a certain point, worse, worse and worse and worse, okay? And you can see that the line that separates basically these two behaviors is exactly this collision point. So this collision point, it seems to have a lot of meaning also from a fundamental perspective, right? This is a very fundamental question, which has nothing to do with liquids or solid in general. Now,
Matteo,
this was the first,
Matteo,
yeah.
Sorry, I didn't quite follow your talk. So you conclude in the previous slides.
Yes.
Slide, like K gap sets the radius of the convergence. Without weakly broken the symmetry, the K gap is 0, right?
Okay, so that's a very good question. So the question is, so if you do Schwarzschild, for example, you will never see basically any collisions. Unless, but remember that you don't see a collision.
The connection, what do you mean the connection?
Sorry, can you repeat again?
So you mentioned for Schwarzschild, there's no connection?
Collision between the modes.
Okay.
So basically what happened with Schwarzschild is this guy.
Okay.
And that's actually why this is also a very important question, which is the following. So you could make exactly the same question you did in this following way. So I showed you before that if you do relativistic hydrodynamics, what you get is a second order, you get a relaxation time, right? This is Israel's Stewart formalism. And if you solve this equation, you get the collision. But then you go here and you don't see the collision. So what does it mean? These things is actually not totally correct. And what they show in this paper, which is this paper here, is that in order to have the full hydrodynamics with also this relaxation time, what you have to add are higher order correction, like Gauss-Bonnet. So the fact that you don't see this relaxation time in Schwarzschild is due to the fact that you are working basically at infinite coupling. And therefore, this is totally suppressed. So basically, when you start doing correction like Gauss-Bonnet, you can see the details in this paper. A relaxation time appears exactly like that. And the relaxation time is proportional to the Gauss-Bonnet coupling. And basically, instead of this, you will start see something like this. Was it clear?
Okay, I should look at these papers.
Yeah, this paper here is the good one.
Thank you.
No problem. Okay, so now let's go to, whoa, I have to be a bit fast. So now we want to do a bit of viscoelasticity, right? So we knew, and we discussed a bit yesterday, how to basically match together these things. So we know that if we take our black hole generically and we compute the response, this is like a fluid. But I showed you yesterday basically how to attach springs on this black hole, right? Using these scalars, for example. And now what we want to do is we want to test how does this behave. So the same experiment that I was telling you before of shearing basically a system can be done in a black hole. So in a black hole, we want to shake the black hole. And how we shake a black hole? Well, deformation, so the mechanical deformation is nothing else than basically a gravitational wave. So whenever a gravitational wave passes through a black hole, the black hole is deformed, right? That's exactly, for example, how we detected gravitational waves. And that's exactly what we're gonna do. So here, what we're gonna do is we're putting a gravitational wave, HXY, which has a profile which is time dependent. And the time dependence we choose is exactly the kind of time dependent, periodic time dependence. And then what we want to see is how the stress tensor react to this guy, okay? So we will do exactly the analogous of that experiment, but in our holographic framework. Notice that this is a difficult problem because this is time dependent. So you have to solve a set of PDE, but it's doable. And this is what we get. So let me show you first a bit what happened here. So first of all, here, what you can see here is an example of G prime, G second, and the angle, the phase. So let's go at zero frequency. So at zero frequency, we know that the part G prime is basically the shear modulus. That's what we discussed yesterday. So here you see your finite shear modulus, which controls the elasticity. And on the contrary, we know that G second starts linearly with the frequency, right? And the coefficient is the viscosity. And that's exactly what you see here. You see a linear shape, and that's what set the viscosity of my system. Now, of course, you can do full frequency dependent, and you see two important things. So the first thing that you see is that a large frequency, actually, the imaginary part goes to 0, and the real part stays finite. This means that the system is elastic. It's not dissipative. And this is in agreement with what Frankel was telling us at the beginning, that if you go to very high frequency, no matter what you are considering, this looks like a solid. And that's very true. Now, the larger we make the graviton mass, the more elastic or the more solid our system. And this is explained here. So you can see at 0 graviton mass, G prime is basically 0 at 0 frequency. This means that there is no elasticity. And then I increase it and I get more and more and more elasticity. So this is showing this plot, for example, G0 is the value of G prime at 0 frequency, and you see it grows with M over T. Okay, so the graviton mass is what determines how solid I am, basically. And of course, if temperature is very big, then I'm melting the things and I'm going to a fluid again. So this model has basically, again, some features which cross over between fluid and solid. And this is what we get when we do one step more. So one step more is the following. So what we are doing here is basically we're plotting the stress in function of the strain. These kind of plot are called Lissajou figures. And what you can see here is the following. So imagine that the stress and the strain are two sinusoidal functions of the frequency. So if there is no out of phase, you will get a perfect circle, right? Because it's just basically a parametric formulation of a circle. So if you see a circle, that means that basically you don't have any weird, let's say, nonlinear behavior, right? Because they're just two periodic things. So on the contrary, and this is what happens when the amplitude of the source is small. So if we put the amplitude of the source is small, this is the kind of answer that we get. You see, the answer is also periodic, and this is linear response. Okay, so this is linear response in the sense that both source and the response are periodic, and the figure is an oval, as expected. Now, if we increase the amplitude, something funny happened. You see that the response stopped to be periodic. So it starts to be very weird and to acquire non-periodic shape. And the Lissajou figures now is not anymore an oval. So you can see, for example, from this is clear that, you know, it starts to bend and do weird things. Okay. And you can see the same behavior basically looking at the power spectrum of this guy. So if you are a small amplitude, we are putting basically a frequency. So we are exciting this system with a frequency which is here. And of course, if the amplitude is small, you see that all the spectrum of the response is peaked there. It means that all the responses are a single frequency. But when we increase the amplitude, you can see that additional modes appear, right? So these are higher harmonics. And these higher harmonics, of course, when you sum all of them together, you get this weird shape, which is not periodic anymore, right? It becomes totally disordered, if you like. Now, why this is interesting? Well, it's interesting because when you go to high amplitude, you go to what is called large amplitude oscillations. And this is a sector which is totally not understood. So there are no theories to basically understand these things, just because, you know, all the linear perturbations and linear viscoelasticity, it's completely of no help because the amplitude is big, you cannot expand. And here what we get is something interesting, which was related also to this kind of question, for example, what are these models? So if you go to the nonlinear response, what you see here is that the G prime and G seconds actually grows with the amplitude. So what happened? It happened that if the amplitude of the external perturbation is small, you can see that the response is more or less constant. This means that the response is not depending on the source itself. So the green function does not depend on the source itself, which is exactly what you expect in linear response. Now, if you go beyond linear response, basically the green function starts to become a function of the source itself. You can think, for example, of the conductivity, right? The conductivity is the current is equal to the conductivity times the electric field. But this is true only if the electric field is small. If the electric field starts to become big, this becomes a total nonlinear function, and the conductivity becomes itself nonlinear. It becomes a function of the electric field. Now, what is funny here is that you see that this response grows. So this means that the more the amplitude that you're putting, the more the system is becoming elastic. And this is something that actually does not happen in metals. It happens in rubbers. So you can see here a sketch. So this is basically the stressing function of the strain. The small amplitude is always linear. This is linear elasticity. But then the metal curves down and the rubber curves up. And these are actually experiments. So the funny thing is that this kind of model looks like the nonlinear behavior is much more consistent with rubber-like material rather than metal. And this was a bit surprising to us. Now, the last part, I will just steal 5 minutes. I want to tell you a bit more about another very curious phase of matter, which it's not yet too clear what it is actually. And I guess it's you have to take it just as some food for curiosity. So glasses. So what is a glass? So this is a big problem, and it's actually called the glass problem. And accordingly to Anderson, is actually one of the biggest challenge of theoretical condensed matter to understand what is a glass. So what is a glass? So we have to go back a little on what we discussed yesterday at the beginning in a solid. And that's why actually I wanted to tell you in a solid to show you this example. So what we said yesterday is that in a solid, we use Debye theory, and the density of states is proportional to the frequency square. Now, what you see in glasses is totally different. So what you see in glasses is that if you normalize your Raman intensity by omega square, so basically this is the Raman intensity, so the density of states in function of the frequency divided by the Debye thing. So if you do this experiment in a solid, you will see a straight line because this function is just basically omega square, okay? Here, what you see in glasses, and this is very universal, you see a peak. You see a peak here, and this appears usually a frequency of the terahertz. And this has nothing to do with the Van Hoff singularity that I was telling you yesterday, because the Van Hoff singularity is set by the lattice spacing and it's at much higher frequency. And what is this? Well, this indicates that there is an excess of states. There is something more. You see, this function is just counting how many states you have at a certain frequency. And accordingly to Debye, it should be constant once normalized to omega square, but it's not. You have many more states here. The question is, what are they? Another very funny feature is that if you take a crystal, as we discussed yesterday, the specific heat grows like T cube, and then it saturates. On the contrary, if you compute the specific heat of glasses, here, for example, is a silica glass, you will find that there is a contribution that is linear in T. And the question is where this comes from, okay? So these are two of the features that goes under the name of low temperature anomalous properties of glasses and are very discussed and still discussed. Now, what happened? So most of the explanations, actually I would say all the explanations so far relies on the fact that the glass is a disordered system. So what is the easiest way to basically discuss a glass? And it's actually what people do in simulations. You take a bunch, so a solid, like a lattice of springs, and you do two things. Either you start cutting springs, random, or you basically start putting the constant, the elastic constant, completely random. So this makes basically the system to be fully disordered. And of course, you can define how much disorder, and the system becomes a glass. So the main reason, the main basically observation in the theory was that you have to take into account disorder. And when you do that, you can explain basically some of the features that I told you. The big problem is that in the last year, some of the properties, actually the same properties, were observed in crystals which are totally ordered and in systems which are incommensurate. So I will discuss much better tomorrow what are incommensurate structures. So this is the point. The point is that in these systems, there's absolutely no disorder, but we see exactly the same feature. So this means that disorder, it might be the cause in glasses, but for sure, it's not the universal fundamental reason behind this explanation. They cannot be the end of the story. And we have to think a bit better. And you know, as theoretical physicists and high energy physicists, we want always to simplify things. So we have to think where does assumption come from? Where does assumptions come from? Basically the idea that phonons behave like Debye. like this. So are we sure that these phonons behave like debye in the glasses? Why they should, right? For example, there are assumptions behind this, right? This starts, as we saw, from basically an ordered crystals. If the crystal is not ordered, why should it be like that? And that's exactly the main idea. The main idea is to discuss the nature of the collective low energy degrees of freedom. So it's very much in the spirit of effective field theory. And the point is that maybe, these phonons look a bit weird in these glasses. And the question is how they look in a glass. Can we make a theory of phonons? So in the last years, I had some fun playing with my condensed matter colleague, try to understand this problem. And we made quite a lot of, let's say, progress. So the first thing that we realized is that damping and harmonicity universally induce this peak. So we made a very simple theory where we compute the density of states, adding damping and harmonicities. And what we saw is that the interplay between basically the debye contribution and the damping produce a peak, simply because the damping contribution wants to grow at low frequency and the debye wants to be basically on the other way. So interpolating between the two, you get basically a nice peak. And the theory also predicts for the first time the density dependence of this peak, and where the previous theories were not able to do that. Now, another thing that we realized is that there could be another mechanism that leads to this kind of bump, and is the piling up of soft optical mode. So imagine you have a system where for a certain reason, some optical modes are very low and are almost at the energy of the acoustic mode. In that way, these modes will contribute a lot. And here you can see, for example, what happened. So here, the only thing that I'm doing is basically I'm increasing the number of soft mode. And you can see that I'm producing basically a big peak in the specific heat and also in the density of states. Another very funny thing that we found is that the linear NT contribution to the specific heat can be given by diffusive mode. So if instead of the debye mode like this, you ask the question, okay, let's imagine now that you have diffusive mode. And let's ask this question, what is the specific heat which corresponds to a diffusive mode? Well, you can do the computation. And what you find out is that this gives a linear NT specific heat. And the funny thing is that this is confirmed by experiment in quasi-crystals. So I will explain tomorrow what is a quasi-crystals. And I will explain you what is a phazon. But basically the phazon is a diffusive mode which appears in these systems. And not surprisingly, in these systems, there are experimental proof that the specific heat is linear. And our claim is that this guy is linear exactly because this guy is diffusive. Now, just to conclude, since I'm out of time, so holography and hydro has been a very successful marriage. And the question is, what can we learn more? And what can we, what can we add also to this hydro? How we can deform this hydro, right? For example, we saw very interesting talk by Yawen before, where we can basically modify this hydrodynamics in certain way to add new feature. And we can ask, of course, the question, what is the dual in holography, or what holography can tell us about this, right? And of course, there are many more questions. Most of the questions are related to the addition of elasticity and the interplay. The second question is, of course, related to broken symmetries or new symmetries in general, like, for example, emergent topological symmetry or breaking rotations, space-time symmetries, or, chiral hydrodynamics, et cetera, et cetera. One other things which I think it's also a formal development, which in the last year is very popular, is finding an action for hydrodynamics. And holography was a key spectator in these things. And another thing which I think it's very relevant is to understand better the physics of open system and dissipative systems in terms of black hole. So if we think about a black hole, the black hole by itself, it's a dissipative system, right? It's an open system that throw away things and absorb stuff. So it's not so illogic that the physics that we will get looks like basically dissipative open systems. Now, the other thing which I found at least very curious is that this K-gap, this collision and this momentum at which basically things start to propagate is basically everywhere. And there are lots of open questions. So we recently published this review on physics report where basically we summarize all the instances and all what is known about this K-gap. And I found it quite funny, and I was a bit like disappointed because we couldn't find the fundamental reason behind. So it's clear that this K-gap has something to do with dissipation. But I would like to know really, you know, some kind of fundamental. And that's why basically this paper that I was mentioning by this author, I think it's this paper here, it's a first step to understand because it's based on symmetry. And I think it could be a, you know, a nice direction to understand much more generally the physics of this K-gap. And finally, about glasses, I think it's very interesting to understand, for example, if holography or if gravity in general has something to do with glasses, right? And if these properties of glasses are really anomalous or are just, you know, can be understood from simple principle like symmetries or mode. And as an aside interest, since in this conference there is also, you know, a lot of gravity going around, I found it quite funny that actually the recent techniques to study Hawking evaporation, page curves, and the information paradox relies exactly on the idea that maybe gravity is an ensemble like glasses. So the methods that these people are using are exactly the method that the glass community are using, basically replica tricks and summations on ensembles. So it's kind of funny that gravity looks like behaving kind of similar to glass. So this is just, you know, a side comment, which of course is at this stage very blah, 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 but I find it interesting. And I think I'm done for today, so I'm open for questions and discussing with you.
Okay, thank you very much for this very nice talk. So do you have any questions or comments?
May I ask a question? Previously, you showed an effective action with two fields. Can you derive some hydrodynamic equation from that effective action?
Good question. So actually, let me see. So this effective action here.
Yes.
So if you look at the modes of this effective action, so basically you solve it and you go, for example, you compute the green function and you extract the pulse. The pulse looks exactly identical to this. So that's actually how we built the field theory. So we built, what we wanted to know is which field theory gives this behavior. So in this field theory, basically, if you go at low momentum, what you will see is basically the physics of diffusion. And it's quite interesting. Actually, our field theory, it's a very simplistic model. If you're interested in much more, let's say, formal and, you know, complete model for hydrodynamics, you have to look basically at these kind of techniques. And I highly suggest the lectures by Paolo Glorioso and Dong Liu about action for hydrodynamics. So in those lectures, for example, they show an example how to write in this formalism the action for diffusion. So they write down a formal action, field theory action for diffusion mode. And there you can derive exactly hydrodynamics from basically an action. But that's a big topic and it's quite complicated because it involves a lot of technicalities. So I don't have time, and actually I'm not expert at all in the topic to give a lecture or say anything profound about it. But I highly suggest that lectures. You can find it in archive. It's a Glorioso Liu lecture on, I don't remember exactly the title.
I see, thank you.
Welcome.
Matteo?
Yeah.
So why holography can enter here in this game?
Okay, you mean why I want to use holography?
Action.
Oh, okay. Well, because of this you know, when at the beginning, when we were asking, for example, what is the action for hydrodynamics, I was expecting somebody of you to tell me, well, we know the action. It's the Einstein action, right? Einstein action on the boundary field theory gives hydrodynamics, so there's no problem. So in that sense, it's nice to see holography as an action for hydrodynamics, if you like. The point is that, of course, as an action, it's very non-local, right? Because hydrodynamics appear at the boundary and it's not very clear. But in principle, that's what the holography is, right? That's what ADS Einstein, let's say, it is at the boundary. So that's why I see holography as some kind of, action for hydrodynamics. Of course, it's not a standard field theory. It's not the standard field theory that you will write. We have a lot of ingredients. We have an extra dimension and blah, blah, blah. Did I answer?
I thought in other way that this hydrodynamics is just a conservation law, and the holography is one theory which should also follow the the conservation law. So, I mean, hydrodynamics. No, holography can mean the hydrodynamics, but not the inverse, right? So
yeah, of course, holography is much more general.
Right, and so holography contains hydrodynamics, but
I agree.
It is not just all. I mean, the hydrodynamics is not everything. So now,
well, I agree, but there is also a comment to say that recently people are trying to resum hydrodynamics and go to very high order. So the claim is that if you resum the hydrodynamic expansion, you get also all the quasi-normal mode, which are not hydrodynamics. So this is an open field that people are working on. But if it works, it might be that actually hydrodynamics, once resum, it knows much more than what you expect. So what is shown in explicit computation is that you take your hydrodynamic expansion, but instead of stopping at the first term, you go very high. So you go, let's say, to 100 terms, 200 terms. And then what you do is you do a border resummation of this series. And what you find out is that basically the resum hydrodynamics knows also about basically the poles, which are totally non-hydrodynamic. So they are at high frequency, at high momenta, but hydrodynamics, once resum, knows it. Actually, with Alex Buchel, we had a paper and we found out also something very funny, that not only hydrodynamics knows about these poles, which are not hydrodynamics, hydrodynamics, when resum, knows also about unstable poles, which are on the upper plane at very far K and omega. So it looks there's something on. That's why it depends a lot on, I was being careful at the beginning with the name hydrodynamics, because it depends always what you mean by hydrodynamics. Hydrodynamics is a term which is used in very different contexts. And I totally agree with you that if you consider only hydrodynamics as an expansion and as conserved quantity, you cannot get anything else than basically the hydrodynamics mode, while in holography you can get all the quasi-normal mode. But if you resum it, I'm not so sure that the statement is still true.
but I don't know. Maybe it depends on how you constructed higher order expansion of the hydrodynamics. But I guess that whatever you sum, conservation law cannot reconstruct the UV structure of the A theory.
Mm-hmm. Well, it depends which system you're looking at. You're right. Of course, if the conservation law is brutally broken.
You're right. If you are looking at only low energy mode of anything, then maybe hydrodynamics is everything. But
no. What I'm saying is that if you don't break the conservation law, but you go at higher order in the hydrodynamic expansion, hydrodynamics does not capture only the first mode, but it actually captures all the modes, basically. If you don't break the conservation equation. Of course, if you put the terms like, let's imagine momentum dissipation, and you make this momentum dissipation very strong, then hydrodynamics is not even the starting point. You will not learn anything from hydrodynamics.
Yeah, right.
That's clear, yeah. Indeed, in this paper that I was mentioning here, there is one assumption which is very important. What it is here is that this breaking has to be soft. You can see in the title, with weakly broken symmetries. So if the symmetry is broken softly, you can still define what they call quasi-hydrodynamics, which is basically a regime where it's not exactly the standard hydrodynamics, but you can still do a treatment. If this guy is large, this is not even an approximation, because you see, I mean, it means that you have to add all the other terms, right? So if this tau becomes very small, which means that the symmetry is broken very badly, then of course you are not allowed to put just 1 over tau. The thing is much more complicated than this.
All right, thank you for a nice presentation.
No problem.
Okay, then other questions or comments?
Sorry, I have a question.
Yes.
So I think relaxation time is a property of 2-point function. Is it true?
The relaxation time, you're saying?
Yes, is a property of 2-point function or grid function. Then so
True.
in holographic models, so can you consider or discuss relaxation time for massive vector or massive spin tensor? 2-point function.
Let me see. So in general, the relaxation time is exactly, so in holography, what you do to define the relaxation time is basically, let's take, for example, this plot, right? What you look is, you look at the imaginary, you take your green function, as you say, and the green function can be the green function of whatever operators you have in mind. So it can be a current, it can be a spin 2, it can be a 2-form, it can be whatever in principle. Of course, you need a model. So, first you need to create a model, but assuming that you have a model, then you compute your green function for the operator you have. And then what you see is you see a bunch of modes like here. And then basically the relaxation time is nothing else than the imaginary part at 0 momentum. So you can see, for example, this guy here is a diffusive mode. So the relaxation time is 0. And this guy, on the contrary, has a finite relaxation time, which is more or less 30 in these scales, et cetera, et cetera. So basically this tells you that the relaxation time for this guy, it's very small. So basically this guy decays very fast. On the contrary, these guys live longer than the other. So there is a very concrete way to define the relaxation time from the 2-point functions, which are actually these computations. So when I show these plots, these are 2-point functions. I mean, these are basically the poles of 2-point functions. So you are totally correct. And if you go to real time,
is it 2-point function? What field?
Well, so here I'm not showing the details, but basically these guys, so let me see, can I write here maybe? So do you see what I'm writing or not?
Now I can.
Here, can you see?
Yes.
Yeah, so basically the green function is something like, okay, now I don't know, where basically, you have some poles here that looks like, I don't know, something like, something like this, okay, very naively, where plus, let's say, usually the structure is something like this. Okay. Right, so this is the usual structure, for example. Okay. This is the usual structure of a green function. Of course, there are many of these. So this is a sum. So yeah, I should write something like, this is a sum on these guys. Okay, so you have a sum of a lot of these poles with a number which actually is not 1. This is actually the residue, what is called the residue. And what you do is basically you do an expansion of these guys and you find out all the modes. Now, when you have these modes, so what is plotted here are basically these modes here. This mode, let me see, let me put it in red. This mode, jam. Okay, anyway, probably you can see, so this mode here. And this gamma k here, if it's constant, so if gamma k, the first part which is constant is basically 1 over the relaxation time. Okay. And this computation is a 2-point function because G of omega k is basically, so G is basically the 2-point function of whatever operator you are considering. Now, in general, in holography, it's a bit more complicated because you don't have only one operator. So you have a bunch of operators. And then the green function becomes basically a green function, a matrix, if you like. And then you have to work a bit harder because you have coupled operator. But imagine you have only one operator, then it's simple. Then the green function is just the 2-point function. And you will see this thing. So then if you go to the 2-point function in time, what you will see is that basically the usual things that we are used. So the relaxation times means that this is an exponential of minus t divided the t relaxation, basically. That is the statement that there is a mode which dies with this relaxation time. So that's exactly what basically these plots shows.
And I think generally this relaxation time depends on the operators or?
You mean in general? So these relaxation times depends on the system you are considering. So You know, if you want to know, for example, how these guys depends on, I don't know, temperature, charge, I don't know, magnetic field, or whatever, these are details of the system.
Oh,
This is, for example, if you have a system which is not holographic, this will come from microscopics. You need microscopics to know this thing. So, for example, if you do the Drude model, which is basically a phenomenological model, you don't know what is this relaxation time. But the important thing is that even if you don't know, you can extract a lot of information. So, for example, you can extract that if this is the relaxation time of momentum, you know immediately that the conductivity is basically rho square times tau, basically. You know it immediately. So, and of course, you don't know what is tau, so you cannot say anything about, for example, how this goes with temperature, but you know that it has to go like this. Did I answer?
okay.
Hey, if you want more, we can discuss offline maybe after. Anything else? Doesn't look like. Okay, then tomorrow we will do more funny things. So there will be more interesting phases of matter, which I recently studied. So be tuned.
Okay, so if there's any more questions, let's thanks to Matteo Baggioli again, and let's call it a day.
Perfect.